A video lecture for session 3.3. This is for MSc 1105, and my name is Jorge Harry Young. And so the objectives for 3.3, we're going to determine even and odd functions from a graph. We're going to identify even and odd functions from an equation. We're going to use a graph to determine where function is increasing, decreasing, or constant. We're also going to use a graph to locate local maxima and local minima. We're also going to use a graph to locate absolute max and absolute min. And then we're going to skip number 6 and go to number 7, which is find the average rate of a change of a function. So we're going to determine even and odd functions from a graph. And so a function f is even if for every number x in its domain, the number negative x is also in its domain. In other words, f of negative x is equal to f of x. A function f is odd if for every number x in its domain, the number negative x is also in the domain. So f of negative x is equal to negative f of x. A function is even if and only if its graph is symmetric with respect to the y-axis. A function is odd if and only if its graph is symmetric with respect to the origin. So here we have three functions. So determine whether each graph in figure 17 is a graph of an even function, odd function, or neither. And so we can see A is actually an even function because it's symmetric with respect to the y-axis. And C is an odd function because it's symmetric with respect to the origin, and B is neither. And so now we're going to identify even and odd functions from an equation. And so we're going to determine whether each of the following functions is even, odd, or neither. Then determine whether the graph is symmetric with respect to the y-axis or respect to the origin or neither. So here we have A, f of x equals to x squared minus 5. B is g of x is x cubed minus 1. H of x is equal to 5x to the third minus x, and then D is f of x equal to absolute value of x. So the first one, to determine if f is even, odd, or neither, we're going to replace x by negative x. So f of x is going to become f of negative x, which then becomes negative x squared minus 5, which is equal to x squared minus 5, which is the same as f of x. Since f of negative x is equal to f of x, the function is even, and the graph is symmetric with respect to the y-axis. For B, we'll replace x with negative x, so it becomes g of negative x, which is negative x to the third power minus 1, which is negative x minus 1. Since g of negative x does not equal g of x, and g of negative x does not equal negative g of x, which is equal to negative x cubed minus 1, which is negative x cubed plus 1, the function is neither even nor odd. The graph of g is not symmetric with respect to the y-axis, nor is it symmetric with respect to the origin. Next one, we're going to replace x with negative x. So h of negative x is equal to negative h of x. Since h of negative x is equal to negative h of x, h is an odd function, and the graph of h is symmetric with respect to the origin. For letter D, f of negative x is equal to the absolute value of negative x, which is equal to f of x. And since f of negative x is equal to f of x, f is an even function. It's symmetric with respect to the y-axis. So we're going to use a graph to determine where a function is increasing, decreasing, or it's constant. So here we're going to determine the different, whether it's increasing, decreasing, or constant. So, increasing means, let me go back, sorry. Increasing means that from x1 to x2, y1 will be less than y2. And so here you can see from negative 6 to negative 4 that the function is decreasing. And the reason being is that 0 is greater than negative 2, negative 6 is less than negative 4, and so it's decreasing. And then from negative 4 to negative 2, again, negative 4 is less than negative 2, negative 2 is less than 2, so the function is increasing in this interval here. And then we go from negative 2, 0 to 0, 4. Negative 2 is less than 4, negative 2 is less than 0, 0 is less than 4, so the function is increasing. From 0, 4 to 3, 4, the function is constant. And then from 3, 4 to 6, 1, the function is decreasing. Again, 3 is less than 6, and 4 is less than 1, so therefore the function is decreasing. So here's some definitions. A function f is increasing on an open interval I if, for any choice of x1 and x2 and I, with x1 being less than x2, we have that f of x1 is less than f of x2. A function f is decreasing on an open interval I if, for any choice of x1, x2, and I, when x1 is less than x2, we have that f of x1 is greater than f of x2. And then a function f is constant on open interval I if for all choices of x and I, the values of f of x are equal. And so here again, you can see an increasing function. Here's my x1, here's my x2, f of x1, f of x2. x1 is less than x2 in the interval, and f of x1 is less than f of x2 in the interval, so f is increasing on the particular interval. This another one here again, you choose an x1 and x2, with x1 being less than x2. And then in this particular example, f of x1 is greater than f of x2, so f is decreasing on this interval. And then for this one, again, you choose an x1 and x2, with x1 being less than x2. And here we can see that f of x1 is equal to f of x2, so therefore the function is constant on the interval. We're going to use a graph to locate local maxima and local minima. And so a local minimum in an interval is simply here. You can see that that's the highest point of the graph. That's a local max. And then this will be a local minimum. So let f be defined, a function be defined on some interval I. A function f has a local max at c if there's an open interval in I containing c, so that if for all x in this open interval, we have that f of x is less than or equal to f of c. We call f of c a local maximum value of f. A function f has a local minimum at c if there's an open interval in I containing c, so that for all x in this open interval, we have f of x is greater than or equal to f of c, so we call f of c a local minimum value of f. We're going to use a graph to locate the absolute max and the absolute min. So here, in this, we have the domain of this function is a, b, and so for all x in a, b, f of x is less than f of u. And so here you can see a f of a, u f of u, and then here, of course, v f of v and b f of b. Now, for all x in a, b, f of x is greater or than equal to f of v. You can see that particular function there. And then so the absolute value occurs here at f of u, and the absolute minimum occurs at f of v. So the interval goes from a to b. And so we're only looking for either peaks or valleys within the graph within that interval. And so here we can see that this is the highest point, that's the lowest point. So this is considered an absolute max and an absolute minimum. So let f be a function defined on some interval I. If there is a number u in I for which f of x is less than or equal to f of u for all x in I, then f has an absolute max at u. And the number f of u is the absolute maximum of f1 I. If there's a number v in I for which f of x is greater than or equal to f of v for all x in I, then f has an absolute minimum at v, and the number f of v is the absolute minimum of f on I. So remember, the value of the absolute max or min is the value of the function at that particular point. In this case would be u or v. So do not mistake the two. That's some students make that mistake sometimes. And so here we're going to find the absolute max and absolute minimum from the graph. So here you can see that 3, 6 would be a local minimum, and 4, 4 will be a local. 3, 6 would be a local max, and then 0, 1 will be your local minimum. In this interval here, 3, 1 is a local minimum, and then here you can see that 1, 1 and 2, 1 will be local minimums, and then 5, 4 will be your local maximum. For D, 0, 0 is your absolute min. And then for this one here, it doesn't have an absolute min or max, but it does have a local max, which is 4, 3. And these points are not defined for this function, so therefore we cannot consider this point or this point to be either a local max or a local min. Actually, I'm going to go back to B. I didn't notice this one. So this one, 3, 1 wouldn't be the local min. It would be 1, 2, and then 5, 3 would be the local max. Sorry about that. So the next thing is extreme value theorem. If f is a continuous function whose domain is a closed interval AB, then f has an absolute maximum and absolute minimum on AB. We're going to find the average rate of change of a function. So let a and b, a does not equal b, are in the domain of the function. Y is equal to f of x. The average rate of change of x from a to b is defined as the change in y over the change in x, which is equal to f of b minus f of a over b minus a, and a does not equal a. A does not equal b. So this is really the slope function, the slope equation, if you will. And so this will be your y2, your y1, and then and these will be your x values here. So we're going to find the average rate of change. And the reason we use this is because if this was a linear function, we can just simply use the slope formula to find it. But this is not a linear function, so we don't really find the slope, if you will. We find the average rate of change. So here, this function, we're going to find the average rate of change from 1 to 3, 1 to 5, and 1 to 7. And so for A, we're going to go ahead and find f of 3 and f of 1. F of 3 for this function is 27, f of 1 is 3. My b is 3, my a is 1. And so this becomes 24 over 2, which is 12. So the average rate of change for this function from 1 to 3 is 12 units. For b, again, same function. We're going to find f of 5. We already know what f of 1 is. That's 3. F of 5 is 75. We substitute the values into the equation, and we get that the average rate of change is 18 units. And then for c, we have to find f of 7. F of 7 is 147. Again, we just plug in the values into the equation, and we get 24. So the rate of change is 24 units. The next thing we're going to talk about is the slope of the secant line. So the average rate of change of a function from a to b equals the slope of the secant line containing 2 points, a and f of a, and b and f of b on this graph. So here we can see the graph. We can see the point a, f of a, and the point b, f of b. And then we can see the secant line that it actually goes through these 2 points. So suppose that g of x is equal to 3x squared plus 2x minus 1. We're going to find the rate of change, average rate of change from -2 to 1. Find the equation of the secant line containing -2g of -2 and 1g of 1. And then we're going to draw the graph of g and the secant line obtained in parts b on the same axes. And so the average rate of change for this particular function from -2 to 1 is -1. So we're going to use that information, and we're going to use one of these 2 points and use the point slope formula to find the slope intercept form of the secant line. And so the slope was -1, or the slope of the secant line was -1. And so we're going to use the point -2, 7, and we get that y is equal to -x plus 5. So that is the slope intercept form of the secant line that goes through the points -2, 7, and then 1, 4 for the equation g of x that we were given previously. And so here's the graph of g of x, and here's the graph of the secant line. And that's the end of 3.3. Thank you.